If you have a fear of speed bumps, you'll have to slowly get over it. Today we are talking about parallel lines and triangles. So this actually does connect to our parallel lines that we had in the last unit. But the first part that your notes was having you do was look at some types of triangles. Hopefully this seemed familiar from grade school, but if you needed to be reminded, you were going to your textbook and the glossary, and they're also in this section, I'm sure, where you can find a definition of each of those. I'm not going to write them, so if you need to pause it, then pause it to write them, but I am going to talk through the different types. So our first three, the acute, obtuse, and right, that's how we would label a triangle by its angles, where I could have all acute angles, I could have one obtuse angle, and that makes an obtuse triangle, or I could have one right angle, and that makes it a right triangle. So it only requires one because I can't have more than just one obtuse angle. Think about what that would look like if you had two obtuse angles. I can't have more than one right angle in a triangle. And so if they have one, it automatically makes it that. Of course, if it doesn't have one, then all three of them are acute. The second category is labeling our triangles by sides. So an equilateral triangle is going to have all sides congruent to each other. An isosceles will have two sides congruent and the other one is not. And then a scalene has no sides congruent to each other. So you can see I had to switch those two. I can have a lot of different combinations of classifying it by angles and classifying it by sides. There's not a particular way that it has to go in most cases. Now there are some cases where, like the equilateral triangle, in order for its sides to all be the same, that means that all the angles have to be the same. It's also equiangular, which we'll talk about later. So in order for all the angles to be the same, they all have to be acute. So the equilateral triangle is always acute. But if you've got, a right triangle could have two sides that are congruent, or it could have no sides congruent to each other. So you've got some combinations that make some sense. So to get us to talk about the Triangle Sum Theorem, we are going to look at the angles of these guys. And this is probably something that you remember from grade school, that the angles in a triangle, the interior angles, add up to be 180. But I always want us to go back to why that's true and make sure we're confirming that to ourselves. So one way that we can confirm to ourselves that the angles in these triangles do add up to 180, you can see I went ahead and marked the parts of these triangles that are the actual angle of the triangle, because what I'm going to do, and if you want to try this on your own, you can grab a piece of paper from behind the door. If you're at home, any piece of paper, cut out a triangle, it doesn't matter what kind, and then mark the angles like this. I'm going to rip off each angle, and see, that's why I marked it, so that I could tell that's the angle of the triangle. Of course, you can kind of tell from ripping what part is the angle of the triangle. So I end up with these three pieces for each of those angles in my triangle. And if the sum of the interior is 180, then that means they should add up to a line. They should have a sum of 180, so they're forming a line together. Not a linear pair because there are three of them, but add up to be 180. Okay, so same thing with the right triangle, and these are all going to look similar, but just to show us that it doesn't matter if you have an obtuse triangle or acute or right, that they will all work the same way, that all of those angles add up to be 180. Same will be true of the scalene. It's got some really skinny angles in here. Up so that we have some room. I'm not measuring anything, by the way. I'm using this as a straight edge. And it should be 180 as well. And there could be some human error in there if it doesn't look like it perfectly forms a line, but we should be pretty close because the sum of those interior angles is always 180. So in your notes, we're adding in that Triangle Sum Theorem says that the sum of the measures of the angles of a triangle is 180 degrees. This is talking about the interior angles, so you might note that this is just interior. We will eventually talk about interior and exterior angles of all polygons. So this is only interior angles. The sum measures 180. And this is a theorem that you will need to know by name. So this is something that you will give as a justification. If you have a triangle and the interior angles are x, 2x, and 3x, then you would set up an equation that says x plus 2x plus 3x equals 180, and your justification would be by the triangle sum theorem. I know that the angles in this triangle add up to be 180. Okay, so one other way that we can see that our angles do add up to be 180, this is not in your notes. If you're really interested, you can write it down, but you don't have to. I just think it's fun to know. So this is a freebie. Anyway, fancy proof where we can see that this does have to be true. You know, ripping the paper up, that wasn't super fancy, but seeing formally why this has to be true. So we're looking at proving in this situation that angle 4, 2, and 5 add up to be 180. We have this set up to where we have lines that are parallel to each other. Those are going to help us out and be able to relate some angles that we had last unit with our parallel lines and angles to connect why that would mean angle 2, 4, and 5 have a sum of 180. Okay, so we're going to start with, and I'm not writing any of the givens, I'll talk through them, but I want you to think about why we would know each one of them before I talk through it. So the first thing, we've got AC is parallel to DE, and that was given. It was given in our picture, and it's just marked that way. So we just knew that from the given. Okay, then if I'm going to be talking about something equaling 180, I might start with something else I know equals 180. So I'll start with knowing that this angle up here, this angle ABC, is a straight angle. So by the definition of straight angle, that would be my reason. I know that the measure of angle ABC is 180. I want to talk about these angles being that angle ABC, so then I'm going to go ahead and add in my 1 plus 2 plus 3 would equal angle ABC. And by substitution, now I know angle 1 plus 2 plus 3 equals 180 degrees. So since there were 3 angles there, this took me a little longer. It was more steps. If there are only 2 angles there, then I could just say angle 1 plus angle 2 equals 180 by the definition of supplementary or linear pair. But since they weren't one of those, I had to use, this would be the angle addition postulate. We added them together to equal the bigger one, and then substitution. Okay, so now, if we're talking about 1, 2, and 3, see if you can think about a way that we could talk about 2, 4, and 5 instead. From there, I'm going to say that angle 1 is equal to angle 4. Can you tell why? 1 and 4 there. They are congruent to each other. Hopefully you thought it. They are alternate interior angles, and the lines were parallel. So because the lines are parallel, by the alternate interior angles theorem, angle 1 equals angle 4. Similarly, angle 3 and angle 5 are congruent to each other. Again, by the alternate interior angles theorem, because those lines are parallel. And now maybe we're seeing it, that if 1 equals 4 and 3 equals 5, then I can replace both of them. So by substitution, I've replaced my 1 with 4 and my 3 with 5. And now I've got it. I have shown that angle 4 plus angle 2 plus angle 5 equals 180. So that will be our main theorem today, but we've got one more set of vocab and another theorem that is kind of a piggyback theorem off of our triangle sum theorem. It's not as important, but it's a cool little shortcut. So first, we've got some vocab. We've got this picture here where we would call angle 1 is an exterior angle. Notice that we're talking about the angles of a polygon, not just a triangle. So we actually have exterior angles for any polygon, and it is always created by extending one of the sides. So if I wanted to create an exterior angle over here with angle 3, I could either extend this side on the right, or I could extend the side on the bottom. Either one would be fine, and it would create an exterior angle. So I'm always extending one side. Same thing at the top. If I wanted to make an exterior angle, I could extend the left or the right, always creating a linear pair with the angle that's next to it, adjacent to it. 2 and 3 in this situation, because they are not adjacent to angle 1, but they are interior angles, are called remote interior angles. remote interior. So that just means that they're interior angles, they're inside the polygon, but they are not adjacent to the exterior angle that we're talking about. We don't use the remote interior as often. Now exterior, interior, we use those more, but the remote interior is important for what we are about to talk about. So we've got a similar example down here where we are going to relate that exterior angle with its remote interior angles. So I've drawn, here's a little triangle that I tried to make as close as I could. Looks like our triangle there. We're trying to relate this 3 and 2 to angle 1. So if we think about this, before I'm going to rip it up and show us visually in a minute, but think about what we have that has a sum of 180, because right now your angle 1 and 4 are a linear pair, so they have a sum of 180, but also your 2, 3, and 4 have a sum of 180 by the Triangle Sum Theorem. So if 2, 3, and 4 equal 180, and 1 and 4 equal 180, then how should 1 relate to 2 and 3? So I'm going to take my angle 2 and 3. Again, I marked the little angle so that we can tell which part actually is the angle. And maybe you already guessed it. Well, not a guess. You knew that that would be true. That our angle 1 is actually equal to angle 2 plus angle 3, which again, what I was just saying, if 4 is adds up to be, or sorry, 4, 2, and 3 add up to be 180, and then 4 and 1 add up to be 180, that means that 1 has to be the same measure as 2 and 3 combined. So the triangle exterior angle theorem, this is not one that you have to have memorized. We won't use it nearly as much as the triangle sum theorem, but it is a nice shortcut, and I'll show you why here in a minute. That our our exterior angle, so angle 1, is always going to equal the sum of the remote interior. So our angle 2 plus our angle 3 will always be true. So now we are ready to get into some examples. So with this new information, we are trying to train our brains to where anytime I see a triangle from now on, I'm thinking if I know 2 of the angles, I can find the third. Just like we're training ourselves to every time we see vertical angles, we know they're congruent, linear pairs are always supplementary. So when I'm looking at this and I see a triangle, I'm saying, okay, I can find x because I know that 20 plus 10 plus x has to have a sum of 180 by the triangle sum theorem. If we were justifying, we'd say the triangle sum theorem. Okay, so we've got our 30 plus x equals 180, and so x equals 150. So then from there, since my x is 150, and we have a few options, I'll talk us through them, but once I have my x, I know that x and y are a linear pair, so that means that my 150 plus y would have to equal 180, or y would have to equal 30. So some of you might be thinking the theorem that we just learned, the triangle exterior angle theorem, would work here because y is an exterior angle, is formed by extending one side, and so it should equal the sum of the 2 remote interior angles. So in this case, y equals 20 plus 10 equals 30. Now for this example, that wasn't going to take us any more or less time than finding x first and then using a linear pair. But if you had an example where they just asked you for y, they didn't ask you for x, then it would be a shortcut for you to say, okay, it's 20 plus 10, instead of going through the angle that you didn't have to find y. So that exterior angle theorem is kind of a take it or leave it. We can go through this angle and then find that exterior angle, and that will always be true. Or we can just use the fact we know the exterior angle is a sum, equal to the sum of the remote interior. Okay. For example 2, so I'm actually going to have you, why don't you go ahead and pause the video for a second. I'm going to keep going, so pause the video. Try this one on your own. You can do it. We may work it in different order, but I'm going to start with x, that I know 30 plus 70 plus x equals 180. And you might not set it up entirely algebraic like this, but make sure that we understand how we would set it up, because we will see some algebra here in a minute, some expressions. So I've got my x equals 80. They've got to add up to be 180, so that makes sense. if you're not writing it like this, at least show me 180 minus 100 so that I can see what you're doing with the angles. For y, I can either take my 80 that I just found and set their sum equal to 180 because they are a linear pair, or I could take my remote interior 30 plus 70 equals y, so y equals 100. Either way. And then with z, now that I know y, I can say my 100 plus 40, ran out of room here, plus z equals 180. And z will equal 40. You may have noticed it was not necessary for this problem, but it's good for us to note at this point that there were actually 3 triangles in this problem. You have the little one, and then this medium-sized one, and then the bigger triangle. Sometimes it comes into play that we need to use the bigger triangle. So notice that if I wasn't looking for x and y, if it didn't ask for those two, I could have actually found z at the beginning, because for the big triangle, 70 plus, this would be 70 together, plus z would have to equal 180 for the big triangle. For example 3, now we're seeing some expressions. We're using the same concept though, so seeing that by the triangle sum theorem, my 90-degree angle plus 2x minus 1 plus 6x plus 5 would all have to equal 180. You could also notice at the beginning that if this equals 90, that means we only have 90 degrees left. So these two angles do have to have a sum of 90. From here, that means that your equation would just look like this, because that's what we would get if we subtract 90 from both sides. So either of these equations is great to start with, and then we'll go ahead and solve for x. Let's see, we're going to get a decimal here. 10.75, just leave it like that since it terminates. So I know we always feel a little bit uneasy when we have decimals. We might plug it back in and double check. Even I'm thinking, I don't know if it was a decimal to begin with. Subtract from 1, that would make this angle 20.5, and it would make the other angle 69.5, and those angles added up together to equal 90. So we're good to go. That is the value of x. As always, be careful to note what your question is asking you, if it's asking for x or if it's asking for a particular angle. Okay, last example. We've got a ratio. The ratio of the acute angles in a right triangle is 1 to 3. What are the angle measures? Okay, so I don't know that we've, I can't remember if we have talked about ratios like this before. I know we've seen problems where it will say one angle is twice the measure of the other one, which this is the same concept. It's saying one angle is 3 times the measure of the other one. But my clue to you, my hint, would be anytime they tell us a ratio like this, that what it's saying is that whatever the first angle is, the other one is 3 times that. So I would put an x next to each of these as if they were, these numbers were the coefficients. So one of these angles is going to be x, and the other angle is 3x. Just to make sure we understand ratios, this would be like if you have 1 blue M&M to 3 red M&Ms, that means for every time you have 1 more blue, you're going to have 3 more red. So you can multiply it by anything. If you've got 4 blue, that means I multiplied it by 4, like a fraction. If I multiplied this by 4, that means I have 12 red. If I've got 5 blue, I would have 15 red, and so on. So what we're trying to figure out is what is that multiplier that we're multiplying them both by to make the angles make sense. So this is the x is what are we multiplying it by. Okay. So if we're looking at the acute angles in a right triangle, we already know the third angle is 90 degrees. For this type of question, they would either have to tell you something like that, it's a right angle, or maybe they'll say the third angle is 120 degrees, something like that, where we have something to go off of. Or they could give you an extended ratio where they would tell you like 1 to 3 to 7. The three angles are in that ratio. It's called an extended ratio. And in that case, we could call them x, 3x, and 7x. Again, just using those as the coefficients, saying, I don't know what we're multiplying by the ratio by, but I know they would be represented in this manner, and then we could figure out what we're multiplying them by. Okay, so that didn't have to do with this problem. I digress. Okay, so now we've got our x, 3x, and 90. By the triangle sum theorem, they have to have a sum of 180. And just like we could have done in the last problem, I could have said x plus 3x equals 90 because that's what I have left over. So we're going to start with that anyway. Subtracting 90 from both sides. We get that the x is 22.5. And then in the end, we're looking for the angle measures. So I want to go back to the fact that if x equals 22.5, that means that one of the angles is 22.5. The other angle is 3 times 22.5. And then, of course, 90, if we're looking for all three. So my 3 times 22.5 is going to end up being 67.5. So our three angles are 22.5, 67.5, and 90. Alright, so again, anytime we see that ratio there, go ahead and write. I'll have an x next to it. And this first number doesn't always have to be 1 either. You could have a ratio that's like 2 to 5, and that would just mean that you've got 2x and a 5x. We're multiplying them both by the same thing, but we don't know what. That's what we're using the equation for.